So let's solve it that way. People refuse. Motion of a charge. Shebi, you are who is talking? Are you with your physics textbook? Anybody with physics textbook? Okay. So motion of a charge, right? Do you remember that we once said that force is equals to QE? Do you still remember? Then you also remember, for those of you that just resumed today, people like Joanna, those of you that just resumed today, last week we are not up to 20. Yes, so please check their notes, give space. So you don't just start and think we started today. No, give space and start. So please, motion of a charge simply talks about the movement of a charge in a field. And I told you what electric field is. We've defined all these things. Movement of a charge in a field. So under motion, once we are talking about motion, I know you are in a haste to write, but today's one is to take formulas, not really to write. So under motion, we know that we always look at acceleration, velocity, and displacement. But the extra to this is that we are going to be having what we call kinetic energy to it. Since it's moving now, since something is moving, if something is moving, kinetic energy also talks about energy of a body that is in motion. So these are the 4 things to have in mind when you are treating motion of a charge. This class is noise. This is my class, not your own. This is not even your lecture hall. So please, less the noise. So if I'm treating this, I'll simply get the same protocol. Force is MA equals to QE. So let's just note formulas. Making a subject of the formula, I will be having QE over M. Equation 1. That is the motion of a body when you are asked to find acceleration. So A equals to QE over M. The second one is velocity. The second one is velocity. From the first equation, kinematics, you remember that we said something about velocity equals to U plus AT. Do you still remember this formula? So at this point, we are taking it that is from rest. The charge is at rest. So at that point, stationary, 0. So V is simply equals to AT, which means that V will simply be equals to carry everything here for EA, QE over M. You see that genetics already used a lot of time, so we'll be fast. That's the formula for velocity. Whenever you are asked to find the velocity of a charge, the speed of a charge, motion of a charge, I did not say distance of a charge, so that you don't stress yourself, just remember this thing. I wanted to skip it because it's too simple, but just so you don't forget, that's why we are treating it. I know that everything we are doing in this class, or should I say with you people, is like film. Before you know it, you are through with second semester. You are in 200 level. It's not your effort that will call the results. Whether you were here for being here, or you are here because others came to class. So you have to be in class. Tutorial. Can I clean? Using the same approach. Okay, no. S displacement is equals to, but please mind you that I once told you that in circular, whenever something is moving in circular form or rotationally, displacement is theta. Is it not true? And that whenever something is not moving linearly, is moving at an angle, that distance is R. Do you remember? And I told you displacement and distance, they are the same thing, just that this one has to do with direction. Shebi? So if it has to do with circular this, why I'm saying this is that we'll get to talk very soon. And you have to remember that. So if I know that from that law that says UT plus half AT squared, if you remember, that time we did from V equals to S over T, we did S equals to VT. When I say that in reality, what we have is actually U plus V, then T. In first semester now, I gave you like 2 formulas for S. One like this, and the other one. So for that reason, the one I'm using is not this one. This one we use it to derive the equations of motion. Why this one is the equation for displacement. So whenever they ask me to find distance or displacement, I'm using this formula here. Charge at rest stationary times this. If you like, say I'm fast. I know I'm not fast because we've done this. So everything here will get out. So that S is simply equals to half AT square. S will be equals to half, or I put for A, which is, the Q there is for what? The income, the M. Okay, thank you. So you see, this is what we have. When you see it to be written, maybe QET square over 2M is the same thing for distance. So with that said, the last one, which is kinetic energy, from half mv square. All I need to do is to simply do m. The v there is what? QE over m, Shebi, times t away. Then t. Now all square. Is it not true? Divided by 2. Hope I'm not confusing you. Am I confusing you? Is darkness upon the face of the deep? See, this is half now. M, Shebi, but give me the values for V. Over M, Shebi. Shay, you know that this thing is the same thing as, this T can also come here. Do you agree? Shay, you agree? If you like, don't talk. Then, now you know. So that is for motion of a charge. We are done with that. Motion of a charge. Very quickly, let's do electric dipole. I want to claim. I told you we've not started solving. You note the formulas. There's nothing we are doing here. Anyone that requires me really explain, I will explain. So once we are done with this, we are going to electric dipole moment, tug of a charge. Then from there, we move to application of Gauss law. Then charge distribution. We solve the remaining questions on chapter 2 exercises. We call it a day. On Tuesday, we start capacitor. Chemistry tutor will be available on Tuesday. He couldn't make it today, but he will be available on Tuesday. That is Prof. And I've sent you YouTube videos under chemistry, solutions, and the rest, so that you start watching. But I noticed that a good number of you don't use your data for YouTube. You use your data for WhatsApp. And it's not like anybody is chatting you. You just scroll up, you scroll down. You scroll down, you scroll up. Time will be going. Electric dipole. Electric dipole. Okay. In physics, we represent this with P. But in chemistry, you always see this to be like this. And advanced, I said, in physics, we normally represent this with P. But in chemistry, you see this like this. That is why that time they will be teaching you polar and non-polar bonding. They will be telling you, if it has, for example, if this is hydrogen fluoride in chemistry, but we are doing physics, they will tell you which one has more electron between the two. Fluorine, Shebi. That means why this one has less electron, Shebi. He doesn't even have he has just one. Is it not true? Let's just say it's one. Okay, let's just say it's one. But this one, fluorine, has like 7 on the outside. Is it not true? So it's easy for this -7 to drag this one. So we say that this one is more polar than this. And at the end of the day, we say that it's a polar compound. But a situation whereby you have chlorine, the two are equal charges. We say they are non-polar. This thing will help us so that you can now see that it is moving from positive to the one that has negative. Is it not true? From positive to more negative. So that means that the same concept is used in physics. We say that the direction of electric dipole is from positive charge to negative charge. You might see it as objective question. That is different from when they tell you dipole moment. I said electric dipole. The direction of the electric field is from positive charge to negative charge. But if they tell me dipole moment, if you notice, I'm giving it to you like tips because these are objective questions. If they tell you dipole moment, this one, the electric field moves from negative charge to positive charge. Somebody might want to tell me now what is the difference. The difference is that this is the thing. Just like I told you about electric field and electric field intensity. Is it not true? I told you electric field is the region where a charge creates in order for a test charge to be influenced by it. I gave you different definitions that day. So the same principle, I now said that electric field strength talks about how strong or weak or what happens in that electric field. If you've not been attending class, check their notes. So the same principle, dipole is the thing. Dipole moment simply talks about the strength of this dipole. Are you seeing it? So that strength of the dipole is what you call dipole moment. And it is this dipole moment that you use to do the calculation, the mathematical aspect of it. Am I too fast? Dipole. I said the electric field moves from positive to negative. Dipole moment moves from negative to positive, Shebi? But I've not defined it, right? I'm not saying that dipole. If you remember first semester when we did couple, we said couple are two equal but opposite forces. Do you still remember? Shebi? The same principle here for dipole. There are two equal but opposite charges. Dipole are two equal but opposite charges. One thing about physics is that anytime you're doing something in first semester, in second semester you still meet topics like that, but different concepts. So I said dipole, or you said describes two equal but opposite charges. You've written that. Now, dipole moment describes the product of a charge and its separation. Dipole moment describes the product, or you say the relationship between a charge and its separation. Or separation, you open bracket, put distance, close the bracket. Hope I'm not too fast. Remember I said, how we do it is, we first of all talk about the topic. When we finish, we now solve the questions. And how we are doing it this time, we are making sure we solve questions as much as we can. I said dipole describes two equal but opposite charges. It's just talking about charges that are equal. More like I say, see how we normally do it in physics. If I bring this to be I'm using this to describe a region now. I say let this be the negative part and let this be the positive part. For the fact that I can see that this is the end of this side, this is the end of this side. If this thing is like 3 centimeters, this is 3 centimeters up, this is 3 centimeters down. Is it not true? Equal charges. This is positive, negative. They did not tell me this one is more or lesser. That is what dipole is talking about. But the minute I start to consider, what is the distance from this one to any point on this particular field, let's say to half of it. I'm using half of it. Somebody might say, what of like 2/3 of it? Is up to you. I will go through this before getting to that. So you see so I'm dividing half first. The minute I start checking the distance from this charge to any point on the field, I'm not talking about dipole moment. So the same thing with from this end to this end, dipole moment. You need to note that. So that means that dipole moment given as P is equals to Q times D. Q times D. Somebody might want to tell me, why is it D? Is D not the total here? But you said from here to here, and you said from here to here. If you put these two things together, is it not going to give you the total distance? Shebi? This, from this end to this end, this is trying to show me that the magnitude separating the two are equal. I've not started to tell you what is the measurement here, what is the measurement here. So the approach is simple. The only way for you to show that they are equal is you visualizing it this way. It doesn't mean that I'm working with anything about the distance yet. So note that. Note that. Note the direction as well. Very important. So let me put that in an electric field proper so that we see what it looks like. I said dipole moment describes the relationship between charge and its separation or its distance, or you say it is the product of charge and its separation. Putting this in a field proper, in physics, you see this always like this. You see this always like this. Somebody will tell me, why are you doing this now? You are not trying to put it straight like this or put it like this. I will tell you why as we progress. Reason is because in this field, if you remember when we talked about charge, we said that charge moves spherical and not linearly, and that it doesn't cross, if you remember. So if it's spherical, it means that whatever charge I have, even when it's like this, I'm expecting it to turn. And because I'm talking about dipole, the net force here, since this is minus q and plus q minus q, is it not going to be 0? So if there's force here minus force here, will it not be 0? So the linear force on the dipole is equals to 0. So that means that if I'm considering this force, it will be 0. So I have no reason placing it this way or placing it this way. I have to put it an angle because the only thing I'm going to be looking at when I'm talking about dipole is the torque. And torque is simply force on a body rotating, if you remember. So the force I am considering when I'm talking about dipole is torque, not force, not F, because F on the dipole is 0. So that's why you always place it at an angle. So force to consider when you are talking about dipole or dipole moment is torque. Note that. So for that reason, you've noted this. Now, you know that F will be 0. And if that be the case, let's find the torque. Since we said that it's torque that can work, that means torque simply talks about if I'm taking this, or if this object now, this charge is turning like this. If it's coming here, this one should be going here now. If it's coming here, this one should be going here. Moving this way. So that is what torque is, the force on the object, on the body when it's rotating. So if I know that, I'll remember that torque naturally, first semester, we said that torque is equals to force times distance. Is it not true? And it's always at an angle, either sine theta or cos theta. Is it not what we said? Do you remember? If it's FR, it means that it's actually sine 90. Is it 90? Shebi? Remember I told you, if it's sine, look left. If it's cos, look right. So 4 and 4 over 4, take the square root of 1. So if it's like this, it means that the angle is 1. But what of a situation where the angle between them is not 1? So in that case, we normally consider it to be at a point, at any point at all. You can choose any point that you want, but I am choosing towards the center. I'm choosing if I turn this thing now and get to the center. So let me place my D here. I'm choosing if I turn this thing and get to the center. What do I have? So in that case, I'm considering this angle to be theta. Somebody will want to say, why are you doing that? I told you it is normal in physics to always consider the angle to be with the horizontal. I once said that even when they give you anything that doesn't make the angle to be with the horizontal, find a way to make it to be with the horizontal. That is the reason why I taught you ASTC in first semester. Away from the angle, use sine, towards the angle, use cos. I'm not going to do any first semester work. I'm running from that. So that means from first semester, you already know that anything happening this side in regards to this angle should be, y should be sine theta. Do you remember? Ekachete. Y is always sine theta now. And this thing here is distance. From here to here, is it not the distance? Is it not the distance? But notice that we are talking about towards the center. That means distance divided by 2. I am not confusing you. You just have to pay attention. Now, that means if this is from here to here is d, that means from this end to this end should be d over 2. And this end to this end should also be d over 2. Is it not true? So that means this should be d of, okay, everything here is, everything totally is d. So this should be d over 2, considering the center. While if I'm considering from this end to this end, but I'm not looking at this, so this should be d over 2 cos theta. I'm not looking at this. I'm just trying to use it to illustrate so that you remember that x-axis should be cos, y-axis should be sine. But this is what I'm considering, the center. When you put your own, remember to make space where you go back and draw this one. This is the one I'm working with. So if that be the case, I want to say, considering torque, the arrow I have there is not just arrow. The arrow I have there is not just arrow, but d over 2 sine theta. Am I confusing you? The arrow here is distance now, is it not true? Talk about the center is simply d over 2 sine theta. About the center. If I carry this thing and turn, and this one we have to turn as well. Remember the goal. As we are turning, each turning we are doing, we are trying to turn so that we maintain perpendicular distance each time we are turning. Go back to first semester. If it's confusing you, you chat me, tell me, send me video of moments and talk. First semester, couple. I will send it to you. I have like 2 hours video on that. But you know it's not a lie, I'm sure you know. Have you not watched my videos on YouTube? Good number of them stand up to 2 hours. I send it to you. You use that and watch it. So if I've noted that, now let's check. Let's check. See, let's check something. Let's check something. Let's check something, please. The F here, what is it going to be? Please remember that F normally is equals to QE. Is it not true? Do you still remember? You still remember? F is equals to QE now. But is it only one Q I have here? How many Q do I have? 2Q. Shebi? That means that when I'm considering this, notice as this is turning, I should be considering this one as well. As you remember that I'm trying to turn this talk about the dipole now, not just about one charge. If you want to do it like that, okay, if we don't want to have issues, let's do it this way. For the positive one, I will have force equals to QE now. Is it not true? Then the arrow will now be d over 2 sine theta. Now for this negative one, that is on the negative one, so that it doesn't look as if it's manipulation. Now it will now be the same thing. QE d over 2 sine theta. Who is saying that cos? Who is saying that cos? As this thing is turning, is it not turning with this one? If you like, be doing magic. I never said I came here and I am turning this thing. As this thing is turning about this vertically, I will not kill myself. I've done this thing in first semester. I'm not even trying to stress about how to do torque again. So if you notice, you will see very well that I am having on this one and on this one. So if you now want to get the net torque, the total torque on this, the T net will simply be upward. If you remember that time, we do upward minus downward, or you say plus downward, and downward always carry minus now. Do you remember? Or you say left hand side minus right-hand side. If you remember, you say left-hand side plus, right-hand side plus left-hand side, and the left-hand side always carry minus. If you still remember, first semester work. So if that be the case, for this one, I'm going to be having T net to be equals to QE D over 2 sine theta plus QE D over 2 sine theta, which should be giving me, am I supposed to put minus anywhere? Am I supposed to put minus? Why? If I put minus downwards, that means that what I'm now considering is actually force, no longer torque. As that thing is rotating. Do you used to do, if you are moving here, let's say you are moving, when you are doing circular motion, remember, when I'm doing circular motion, as this thing is rotating, charge moves spherical. As I'm moving circular motion, if I do, this is 0, I know you want me to go like this. Sorry, but because of the fact that positive is moving to negative, that is why I'm going this anti-clockwise. If I'm moving this, I don't used to do, if I get to 90, I will now come and start doing minus 60, minus 30, minus 45, minus 25. When it's circle, if I'm numbering round, I maintain the positivity. So I am maintaining that positivity because I'm considering the charge to be spherical, to be a circle. And when I'm numbering a circle round, I don't number my circle round negatively. Is it confusing? I ask you a question. When you say it's confusing, I expect you to ask questions so that I clear you before we progress. But if you watch what I'm saying, you will see that I know where issues will always come out. And that is why I always leave room for us to debate it. Ask your question. Let me add to what you think. Everything. Let me tell you, it's not everything, it's not for you. If you come now, you say you have a problem, you need your problem to be solved. The first thing they will ask you is, what do you have? If you have nothing, they shouldn't attend to you. So please, somebody that has something, talk to me. It's just like when they kidnapped one guy in Imo State. I was watching a video. Then as they kidnapped all of them, one was saying to the kidnappers, I don't have anything, no. If you check me, apart from this my truck, I am empty. Nobody will call now that will come and save me. They told him, oh yeah, go. As he was going, they stabbed him from the back. It's not good news, Shebi, but it's a lesson to all of us. You don't seek mercy from evil people. It's not like I'm evil, but the cause itself is evil. The cause itself is evil. So why am I saying this? If, peradventure, you find yourself in situations like that, don't go and be looking for pity. It's just like, let's say, one man was carrying his bike to take the wife to a nursing ward, like a place where she will deliver. They collected his bike, criminals. He was telling them, I don't have any other thing to take my wife to the hospital. Please help me. Please forgive me. Please give me the bike back. What did they do? They climbed down from the bike, told him, oh, yeah, carry the bike and go. As he was about to move the bike, they shot him. I'm telling you life stories, so you might think it's made up. Real life stories. You don't expect kindness from evil people. You either find a way to escape yourself or you just keep quiet. It's real. So please, somebody that has option, reasons to call me back on this, tell me what the problem is. Let's progress. It's just what? Okay, because they saw this one. Okay. Okay, it's not the same with this one. Okay. See. Let's take it that we've not done any of this. See. Watch now, watch. That meant that they taught us for couple. What did they later tell us is the tug of a couple. When we want to calculate, wait, I'm no longer doing dipole. That time we did couple. What did they later tell us is the tug of a couple? 2FR, Shebi? Is it not true? Do you know what you are making room for? You are making room for whatever the direction is, be it positive force or negative force, or be it equal or not, provided that you can very well see that the distance separating them, on this end, this one has a ridge top, this one has another ridge down. You might even see this as you progress, work done by a couple, something like 2FR theta, something like that, for work done by a couple. So, but this is not where we are. So why am I saying this? If you are considering dipole as well, you are not considering that charge. If you consider that charge to be positive and negative, that means what you are calling it is 90 degrees. That's what you are calling it. You are no longer saying that it's rotating. And tug is simply force on a body rotating. And why we have to put this at an angle is because we are saying that for tug, we don't consider the negative and the positive. That is why I did not say the tug here and tug here should cancel out to be equals to 0. So provided the body is rotating, if you are drawing circle, you never draw your circle and start numbering. Everything from here to here is the same thing from here to here. Here, near, but the same thing. Naturally, we know that when we punch the sign of it always gives us the one greater than 90 to be negative and the one here to be positive. But in numbering this, do you come and put minus here, plus here? You don't do that. So the same approach is what you are using when you are treating this tug. So simply, in order for us not to be stressing ourselves, I want us now to know that dipole moment is simply QD, while tug of a dipole is simply from 2FR, you now get the tug. This is how I want you to consider it now. From 2FR, you get the tug. So if we know that dipole moment is QD, the same thing with couple, 2FR. Why is it that 2FR? We are taking it that whatever charge is here and whatever charge is here, we are not considering those signs. So for that reason, if I put what F is QE now, is it not true? Then the arrow that I have here is D over 2 because at an angle, the y-axis is going to be sine theta. And notice that it's from the center we are considering this, not like we're saying the full thing here. If we consider the full, it's no longer at an angle. So this is going to be R9 is going to be D over 2 sine theta. Then Su tug. It's not hard. Why it looks as if it's hard is that we forgot first semester work. We did that class at mass communication block upstairs, if you remember. And let me even tell you how we did it. The day we were doing it, that woman that sells buns and whatever came to the class to announce. I told her to leave the class, not to disturb us. So you see, I remember everything well. And before I started that class, Master Atoka taught you mathematics. Yes. Shebi, you remember it now? You, I wonder what you are thinking. I wonder what you are thinking. So, I am correct, and that is how it should be. So, with that said, you can see that if you arrange this properly, this will then give you the sentence as saying 2QE D sine theta all over 2. 2 can cancel 2. So that the torque of a dipole is simply QED sine theta. Now, child of God. Child of God. Child of God. You're not a child of God. This is Q, Shebi. This is Q. This is D. This is D. Can you see the D? Now, that means that this is the sentence saying QDE sine theta is the same thing, is it not true? So I will not be wrong to say that the torque of a couple is the same thing as saying dipole moment times electric field sine theta. I will not be wrong to just say somewhere in my notebook that instead of stressing myself that dipole moment, torque of a dipole is simply dipole moments, electric field, sine theta. Finish. So we are not wrong. This is it. It is still the same thing with couple. The same thing with couple, just that this time around you are not including charge. And then you are making room for the torque at an angle towards the center. So not you using the full length. If I happen to consider the full length, this full length now, you will see that, watch, if I'm turning this now to this point, before it gets to this part, it will be half of it. Then before it gets to this part. So there's no reason why I would jump this half to get to this point. So that is why we said that we always have to make room for it to be at the center when considering it to be at the center, half and half. Since what we are talking about is simply equal but opposite. I don't even know how to define this thing again or describe it. Because you people make me describe. I'll run out of words. Oh, yeah, I want to clean. Can I clean? We have to be fast. It's not hard. When you revise it, it becomes easy. I hope you know that gym is free for tutorial students. Why is it that it's only the same type of people I see in the gym? Some of you don't used to gym. And do you know the worst part? Wait, now let me ask you something. Let's be honest now. How many times do you go to toilet a day? Answer me. It's very important. How many times do you go to toilet a day? Do you know what some people say? Sometimes I don't even go to toilet like 1 week. And do you know what they feel? They feel their own body is the normal body. There are people that go to toilets don't have normal body. Like one lecturer was talking to a student. Calm down, man. Calm down. When I did my NYSC, less the noise. There's one lecturer they normally invite. That is like Ministry of Lands and Survey. He will come there. He will say, that toilet. People that go to use that toilet, I wonder what they are doing. Me, I can stay here for like 1 week. Manje toilet. Normal. In my mind, I was saying, I just said, wow, you are dying. Yes. Because the minute you start doing that exercise, what it does is that it increases your metabolism. The rates at which your body will be, should I say, digesting and removing things from your body will be higher. So, what if you're not eating? But please, try your best to engage in those physical activities. It helps you. You will see some persons in year 1, they are looking very slim. 200 level, they are looking like giants. If you see them, they say, no, it's not exercise. It's because they now have money. It's a lie. If you start exercising, you will not be that big. That's the truth. You must slim down. If you know the amount of calories you burn just doing exercise. And the worst part is that we are living in Nigeria. One bad terminal disease might hit you. Yes, now, because as you are running, you are flushing all those things out. Have you not watched that doctor that said that the reason he's advising men and women to be engaging in certain activities is because it flushes toxin? All those things that he's saying, you can actually flush it during exercises. So please, that is why we made that gym free for tutorial students. So just check the days we allow you to come and gym. You come and gym. I think Saturdays, somebody will say, which Saturdays? You know this Saturday now. What of 6, 7 in the morning? If you call me that you want to come and gym that time, the gym should be open. Where is Bellarmine? He normally call me in the morning that he wants to come and gym. That medicine boy, he will come and gym. So please, take it serious. Take it serious. All right, back to business. I can clean. The next thing I want us to look at, shall you see that this one is looking one kind. Let's now do the last one. The potential energy of electric dipole. Potential energy of electric dipole. Or you say energy of a dipole. Energy of a dipole. So I'm using work done. So it's given by the work done, differentiate, change in work done is equals to change in torque. Okay, yes. Change in torque. Okay, I think it's best this way. Yes. What am I doing? Is equals to torque with respect to the theta. That is with respect to the displacement. So work done is equals to torque change in displacement. Do you know that this thing is the same thing as saying TR? Sure, you know. So, but this is how you view it. Why am I using this? That is how physicists put it. So, you are using that theta. So, if that be the case, if I want to now get energy, hope you know that energy and work, they have the same formula. Shebi? So, work now is going to be simply equals to, if this cross equality sign, it becomes integral. Integral torque d theta. I've not done anything strange. I'm doing just normal things. So I believe Master Tucker is showing you things like this now. He will get there. Differentiation and integration. I have videos on that too on my channel. If you check differentiation, integration is there. So now see. Let's first of all, what did we get torque to be? When we did torque, what did we get torque to be? P sine theta, Shebi? Then d theta. Okay. Do you know that this is a constant? Because if I integrate PE, there's nothing like if you integrate PE, you get another alphabet. Sure, you know there's nothing like that. Are you aware? So I'm just going to bring out PE outside. So I now say integral sine theta d theta. There's integrate sine theta with respect to theta. So now, anytime you see all those things, you know that there's what we call trig ratios. Anytime you see the trig ratios that start with S, once you integrate it, the answer you are getting must be negative. What must be negative? Second, sine. You know that we have tangents and cotangents, cosecant, Shebi. But those ones that have S before it, anytime you integrate it, the result will always have negative. Have that in mind. So, but before I do that negative, I need us to check something. As I'm integrating this, before you integrate this, the rule is simply, if this is dipole and electric field moves from positive. Is it not true? To what? Do you agree? Dipole itself moves from what? Shebi? Somebody will want to tell me, but dipole moment moves from negative to positive. But if you remember, when we started, I told you that this P stands for dipole, but the other one describes what it does. And the other one, whenever you see that one, it will always be that it is equal to QD. And that QD is what we replaced here, I know. But the P I'm seeing here is simply dipole, electric field. So it is simply taking that you are moving, even if it is dipole moments we are considering as well. What he's saying is that if I have something to be positive and it has to give up positive to go to negative, is it increasing or decreasing? If I have to be, remember I told in my last class that men are metals, women are not metals. Do you still remember? Okay, you don't remember. You are not in that class. I gave you reasons. If you remember, in secondary school, they tell you nitrogen, oxygen, Shebi. Is it not true? Ngwasi, combine hydrogen with fluorine for me. What do you get? Hydrogen fluoride. What will happen? This one will lose the last name and take IDE, Shebi. Ngwa, combine these two for me. What will happen? It will take IDE. Is it not true? It's taking a man's name, which is IDE. Shall you see it? This is not meta. This is meta. And who gave out something here? The meta. Now, is it not true? Is giving out electron. Who is accepting electron? The non-meta. Is it not what we have in real life? Is it woman that pay bride price? Or if you say yes in Jesus' name. Okay, but please, the principle I'm trying to introduce there is simply the one that has positive is losing, while the other one that is having negative is gaining. Shebi? That means from positive to negative means loss, decrease. So we now say that same approach, whenever you are considering work, before even solving anything, that you're always going to have a negative sign. That means that everything I did here is simply, somebody wants to say, Jesus, where are they bringing all this stuff from? Yes. That is why they say that this particular course, electricity, is something you do in engineering. You do it advanced level calculation. So please have it in mind. So before even solving this is the sentence I say minus PE integral sine theta d theta. Because of the decrease. I remember in our last class, in our first semester class, I normally tell you that sign does not matter, but still put it to show that there is decrease. You are considering it to be decrease. So if I know this, I can now integrate. So that this now becomes W equals to minus PE, then that sign will become minus cos theta. Sure, you know. Cos theta. So this thing simply means differentiate sin theta with respect to theta. So if I've done that, this is going to be the sentence as saying, now please, before I progress, this integral sign, I can leave this thing like this, but I want to do it in two ways. If you differentiate sin theta, it becomes negative cos theta. If you integrate sin theta, it becomes negative cos theta. I said it earlier. And please notice something. There's one thing I almost missed. Whenever you introduce this thing, this integral sign, as you are differentiating this, you're always going to show if it's a definite or indefinite integral. If it's indefinite, it will just carry plus c. If it's definite, it will have boundary. So it will be like, let's say I have moving from 0 to 1 or from 1 to 2. You get the point? So as I finish this thing here, it's going to be more like saying, hell, Chukunna. Well, see, let me do it again. I said, to integrate, there are two types of integration. Definite integral and indefinite integral. Definite integral is the one that comes with boundary. It will always tell you are moving from lower boundary to upper boundary. Maybe from 0 to 1. From a time of nothing to a time of maybe 2. From a time of 2 to a point 4. While indefinite integral is the one that just comes. If you finish, it just tells you put constant c as your constant. So, but when you are solving in physics, we always make use of the definite integral. We always make use of boundary. So what I'm saying is that this thing can now be that whatever I'm having for this theta, since we said that there is decrease, now there's sign here, is it when it's moving from initial points to final points, or is it a point of, let's say, 1 to a point of 2? I can have a point of 2 to a point of 3, and so forth. So it's up to me to make choice. So why I'm not using 0, why I'm not going to be making use of 0, is for the fact that I am having this at an angle, and they never said that that charge is at rest. So I'm simply going to make use of 1 to 2. If you want to make use of 2 to 3, it's up to you. So if I know this, this can also be written as minus PE minus cos theta. Now I come and put that boundary, 1 to 2. What this thing means, somebody can put 0 to 1. Anyhow you want to put it, there's really nobody questioning you. The 1 and 2 I'm using is because it's what I want to use. If you want to use 0 to 1, it's still valid. Now W will be equals to, now notice something, please watch something. This minus and this minus will do what? Is it not plus? Cos theta 1 raised to power 2. This thing is a boundary. And why I'm still carrying this boundary is to show you now. This is the something I'm saying PE. Okay, when I have PE cos theta, now notice something. I can have this to be PE2, or let's say, yes, PE2 minus, that is upper boundary, minus PE1 cos theta. You can see it in some textbook as PE cos theta 2 or cos PE cos theta 1, whichever place they put it. But in physics, we always regard it to be at the angle. So from angle 1 to angle 2. So this is how you have this W. Am I confusing you? Am I confusing you? Somebody might want to tell me, if it's like this, why is it that you are not starting from 2 instead of starting from 1? You always do final minus initial now. So that is why we have that like that. So sometimes you see it this way, ending this way. And sometimes you see it going further to be simplified. Please, this thing should not confuse you. As you start doing differentiation, you'll be meeting a lot of it. You'll be meeting a lot of it. This thing now simply means boundary. This thing simply means boundary. It's a boundary that is telling you, in physics, we do mostly integral that involves boundary, not the indefinite one. So it's always going to be from, you know, everything in physics is physical now. Everybody has time. There's time for everything. So if that be the case, that means it's definite. There should be a boundary, a range. So if I know this, this can also be given as, now since you know this is work, Shebin, is it not true? Which is the same thing as energy now, done by energy of a dipole. Is it not true? Energy of a dipole. Now notice something, please. Child of God, notice something. I can leave this answer like this. I can leave this answer like this, so, but I can't leave it like this. I can't leave it like this. Do you know why? It's carrying a boundary. Sure, you know. I can also go on to say, since I'm talking about dipole, this energy is decreasing. I can put this to be U. Energy of a dipole is represented with U. Even in physics, energy is represented with U, mostly U. So this is minus U. The energy is decreasing. If that be the case, this is the sentence I'm saying minus U is equals to PE cos in a neighbor. So let's say at a point where this is at rest. This is initial now, is it not true? We can have a situation where it's at rest. If you don't want it to be at rest, I know some people, once this thing we are doing, some persons don't like it. Somebody somewhere is looking at me like, what is this man even doing? Please, bear with me. I just have to take you through this process because there's no other way. I can easily tell you, cram it that it should be this one, we say it's a man, but if you forget inside the hall, uncle, that is why I'm putting you through all these things. So please, they are saying that at a point where this is at initial, and I have it to be 0, our starting point, I'm not going to be left with just PE cos theta. Or if you don't want to do it like that, if you know that, for example, acceleration is equals to v minus u over t. Is it not you that normally write acceleration equals to v over t? Shebi is you. When you write this thing, what you are saying is that you've actually done the subtraction. Is it not what you normally do? If you don't want to consider it to be at rest, consider it that now you've actually done the subtraction. And after doing the subtraction, you now have P equals theta. You get the point now? Now, if you get that point, we are now saying that the energy now, since it's decreasing, making it subject of the formula will cross equality side to become minus P cos theta. Energy of a dipole is given by this side of God. So I can claim is in tutorial class they impregnate you academically. Please and please, if today is your first day, I will advise you, if you're just resuming, check their notes, check all we've done, update your notes. You're not writing. Okay. Please, if you've not paid us for tutorials, you need to pay us for tutorials. Some of you paid us part payments, and each time you still have the mind to come to this hall to check if the man is a wicked man. Please, if you've not paid us for tutorials, stay in your house. I am begging you. I don't want to come to you with time, tell you to stand up. You know that there's how people behave. When you are this type of person that is more or less available, they tend to think you don't know how to do things. The availability is because of people that are naive, people that don't really know what is going on, so that they don't miss road before getting the right information. It doesn't mean that I, at any point, don't know how to take a stand. So I am never going to be doing anything with you and trying to impress you more than you should impress yourself or respect yourself. So please, I beg you in the name of God, if you've not paid us for tutorials complete, start staying in your house. I wouldn't want to come and pursue you one day, and I will be a wicked man. Reason is that good number of persons have paid here. You don't make a fool of us and of them as well. We can't allow you when some persons already paid us complete. We can't allow you when we know that we have certain amount fixed for this tutorial class. So please, I am begging you in the name of God, start staying in your house. You know they do small things. When I was your age or in your class, not like age, in your class, I know that I talk too much. Once I see anybody, I describe that person well in my mind. I have something to say about that person. I have my reservation. I have analysis. So in this age, you people are good with that. So you don't have too much to add to your analysis. Stay in your house. I am begging you. Let's continue. Please, I will not make this, I will not send this thing on Tuesday. Tuesday, I will not send it again. If you've noticed, good number of you will come and meet me. Master Toka told me to just get out of the car. Yes, I'm supposed to be like that too, but I believe all due processes should be observed first. Please, and please, Tuesday, if you don't want to pay us your tutorial fee complete, you don't want to tell me, oh yeah, call my dad or my mom, stay in your house. Please. Applications of Gauss law. Application of Gauss law. So write for me. Gauss law, due to a spherical charge distribution. Gauss law, due to spherical charge distribution. That's number one. I know we've talked about Gauss law, Shebi. We've talked about Gauss law in our last class. So I am not treating Gauss law from the beginning. We know that Gauss law simply says that the electric flux through an enclosed system is equal to the charge inside that system. So what he's saying is that you can't see the amount of charge that is in a system, but how you can tell how much charge is in that system is what is coming out. That is what Gauss law is talking about. Now we are trying to deal with the application. So due to spherical charge, that is the first one. Why I'm using spherical charge first is because we believe that charges move in spherical form. That is the first. So for spherical charge, I have this to be a surface. Let's say this is a surface. Somebody might want me to make it really sphere, but let's do it. Let's say this is a spherical surface. So on a spherical surface, let's say this is the center. Let's say this is the center. Now from here to here becomes R. Now Gauss law is saying that you need to enclose this. So now what we use to enclose this is what we call the Gaussian surface. If you go through your textbook trying to read this thing, it will be very confusing. But once you finish this, you go home and read that textbook again. It will make sense. He said, somebody said what? Ask. Tell me. Ask me. Odagobi, Ngwana, let's progress. It's not me that is doing you. If you have questions, you feel free and ask. Now see, if this is the surface that is having center to the outside, this is the radius. Gauss law is simply saying that once you have this surface, that there are charges on this. Let's say this is a region of charge. Let's say, I told you in my last class that charges tend to appear on the surface. They move to the surface. And as it moves to the surface, it moves to the sharpest point. If this particular thing gets charged, all the charges will want to come to this point. The part that is sharpest and tiniest, that's where all the charge wants to gather, because in itself, it wants to escape. But because of the fact that it's not easy for you to escape, it keeps going around, but much of the charge is at that steepest point. So if I know that, that is what we call action of point phenomenon. If these be the charges, and I told you in physics, positive charge is what you consider as charge, unless they indicate negative. Once you say charge, positive. Gaussian law is now saying, take it that you enclose this into what we call the Gaussian surface. Gaussian surface. Take it to enclose this into what we call the Gaussian surface. It's now saying that if this particular Gaussian surface is outside, it's enclosing the entire surface. You can now see that from this center to this Gaussian surface, the radius R here is bigger, is it not true? So it is not saying that the first rule for a spherical surface, Gaussian law or Gaussian application due to spherical charge distribution. The first one is that when R is greater than R, you can see that the charges, all the charges here, will pass through. The charge that will pass through here, that will be displaced here, will be equal to the charges that are inside here. Is it not true? And we say that for that reason, at that point, electric field will simply be equals to KQ all over R squared. Do you remember that electric field, this is the formula, right? So when this is spherical, I derived this thing in our last class for spherical surface, how to derive it. I derived it using that EA equals to Q over E naught. I derived it where I said put E, then 4 pi R squared. Shebi? Equals to Q over E naught. And I said try to make E subject of the formula. You know, is it R squared? Is it 4 pi R squared? Yes. Okay. So I now have equals to Q over E naught 4 pi R squared. And notice everything here, Shebi, K is equals to 1 over 4 pi E naught, sorry. So everything here, this is like invisible one. So this is everything, the same thing as KQ over R squared. We did it in our last class. Check. So if that be the case, I'm not trying to derive spherical. So I'm just trying to teach you something you need to know. So once you can see that the Gaussian surface is enclosing it outside, it's enclosing the entire surface, you can easily say that that thing Gauss said is going to happen because all the charges here will flow out on this one. It will be equal. The electric field will be the same. So this rule will still hold. Another principle is when you have this Gaussian surface, that is I under spherical, still under spherical. This is the first condition, I. The second condition is you have this, 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 you have this. All the charges on the surface, all the charges on the surface, all the charges on the surface. You will see sometimes they say, they now come and tell you, maybe they put like a charge outside here. What they're saying is that if a charge is able to flow out on this Gaussian surface, it's still the same thing because all these charges that are inside here are enclosed inside here. All the charges here will be here. The same thing with when, let's say the arrow now, the Gaussian surface we have, this is the normal arrow for this surface. I'm using spherical surface. I'm using spherical surface. Reason being that charges move spherical. You can have spherical surface, you can have cylindrical surface. We are still under sphere. So if I know that, let's say the arrow now is no longer outside, but let's say they come and say a charge is placed on this surface, it is still the same thing as saying the Gaussian surface now that you are having. You now say let the Gaussian surface be exactly here. Let the Gaussian surface be exactly the same with the spherical surface. In that case, R for the plane surface, the spherical surface is the same thing as R. You can very well see that all the charges here will pass through. Are you getting the point now? And when all the charges pass through on a spherical surface, electric field will still be KQ over R squared. The last one, the III. This thing is important. You will see questions on it. They will tell you when the Gaussian surface is inside a conducting metal or material, whatever, what will be the electric field? You will see questions, different angles. If you understand it as you go back to read your textbook, it will make more sense to you. We are still under the first application, but the first application has like three sub, or should I say three children. So the III is in tutorial class they impregnate you. Academic. Be playing now. Just be playing. Just be playing. Oh yeah, what? Now what? This is oh God. Oh yeah, this is a spherical surface also. Now, let's say the charges. Somebody will not tell me, why is it that you are saying all your charges are coming? Yes. Once it has to do with charge, I told you in our last class, all the charges always tend to gather at the surface and it moves at the steep point. So it will want to move to the part that will let it out easily. So if that be the case, the third case is where they are now having. Be checking when this thing stops for me. So let's say this is